Hi, the captain speaking, and welcome to Uartek Rover team. Uartek Rover team is founded in October 1st, 2023 in Manisa Celal University. Also, Uartek is an acronym that means spacecraft technologies in Turkish. Although most of us are mechatronics and software engineering students working in every department. For 2 years, we are working on spacecraft and multiplanetary science. The Uartek Rover team is divided into 4 departments. Our mechanics and assembly team handles the vehicle's overall movement mechanism and designs, while the electronic team deals with power distribution, PCBs and electrical wiring within a vehicle. Separate from the others, our computer science team works on software and hardware in areas such as autonomy, robotics and communication. Lastly, our science team conducts analysis in research in natural science, including geology and physics, forming new hypotheses and continuing their studies. We are a passionate team of young engineer students based at Celal University with a keen interest in spacecraft and multiplanetary vehicles. This interest in space has guided us on an exciting journey of exploration. Fueled by our desire to push the boundaries of the space and our passion to excellence, we developed our rover named Barkan to make difference in international competitions. In every project, we combine technology and innovation with engineering skills to contribute to the future of space exploration.
Our rover is designed with a rocker body suspension to ensure stable driving in all types of terrain.
Our rover was assembled using 3D printing technology. We use PLA filament in the connection points of the rover. We also use TPU filament in our tires. This material gives us flexibility and durability.
Our robotic arm is designed for object manipulation tasks. Constructed from readily available hardware parts, 3D printed components and tubes. Currently, the tubes are made of injection molded plastic, but they will be replaced with the carbon fiber tubes we have once the sizes are verified. We chose a modular design for ease of development, part replacement and portability. We also plan to incorporate interchangeable end effector systems in the future, enabling the robotic arm to perform different tasks with ease.
We've designed a quadcopter with durable 3D printed parts to withstand crashes. It takes off from the rover, follows it closely, and takes high-resolution images of landmarks. After completing its course, it autonomously lands back on the rover.
In our rover safety systems, we have a battery management system for balancing each battery cell and preventing over and undercharge. An emergency stop button is available to cut the power in case something goes wrong, and a fuse is included to cut the power in case of a short circuit. Diodes are placed to prevent reverse polarity connections.
The rover's localization, navigation and mapping systems are all connected with ROS2 library, thus we easily connect to the rover systems. To obtain the 3D point cloud data from the Kinect V2 camera, we use a library called FreeNect2. With that library, we achieved infrared, RGB and depth images. Because of this library doesn't have ROS2 capabilities, we developed our own package to interpret depth information for ROS2. After achieving 3D point cloud by the Kinect V2 camera, we used a 3D mapping ROS package called RTAB map for make the information understandable in 3D space. Additionally, with RTAB map package, we achieved visual odometry, which helps our rover to have better localization. For use all these systems with Kinect V2 camera, we developed our own ROS2 packages with C++ and Python. At navigation side, we use ROS2's navigation capabilities. ROS2 navigation system is the control system that enables a robot to autonomously reach a goal state such as specific position and orientation relative to a specific map. Given a current pose, a map, and a goal such as a destination pose, the navigation system generates a plan to reach the goal and outputs commands to autonomously drive the robot, respecting any safety constraints and avoiding obstacles encountered along the way.
The initial phase of the project involving dataset collection discussed with computer science subteam. Photos were gathered from different sources.
In rule flow, each object was manually marked and labeled by our CS team members, a crucial step for the model's learning process. Proper labeling made the model's training more efficient. Once the dataset was prepared, model training commenced. The yellow weight model was used with Python and relevant libraries for training. During training, hyperparameters were adjusted for optimal performance.
Using the model trained with Yola V8, we will detect objects and obtain their names and pixels as a result. With these pixels, we will determine the locations of objects, aiming to center the object relative to the robotic arm.
As Uartek Science team, we have chosen a researching zone as user criterion for understanding the perimeter in geological structure. Because this data suggests it was once a lake with a chance we to have fed it. If it was, it could have also necessary for life, indicating possible microscopic life.
Another reason for choosing this crater is its mineralogical and geological similarity to Lake Salda in our country. Lake Salda's geobiochemical process supports stromatolite formations, resulting in white hydromagnetic stromatolites. These deposits formed by climbed geological structures, bacteria and cyanobacteria dating back 3.5 billion years are considered the oldest fossils. Today, modern stromatolite formations can be observed in Lake Salda. The similarities between the hydromagnetic stromatolites currently forming in Lake Salda and the carbonate rocks on Mars are noteworthy.
Based on this information, we plan to take a rock sample and examine this under the microscope to identify those stromatolites.
With the microvolume spectrometer we have designed, we will gather information about samples, chemical composition and purity. We will also analyze their protein concentrations, nucleic acids, turbidity levels and fluorescence properties. Detecting fluorescence properties will help measure the mineral composition, density and quality of any organic matter in the soil, if present. Nucleic acid analysis will provide insights into microbial presence, biological activity and soil fertility in the field. These measurements are critical for investigating potential signs of life. Essential nutrients such as nitrogen, phosphorus and potassium are critical for life. The correct concentrations of these elements in the soil are necessary for healthy plant growth, so we will determine these concentrations quickly and accurately using MPK sensors. Furthermore, providing suitable weather conditions is important. We will continuously monitor air quality and conditions for both our scientific mission and our drone mission using sensors to track pressure, temperature, and humidity levels. These sensors will help ensure an ideal growing environment, enhancing plant health and detecting the properties needed for executing the drone mission.